Why can't you drink seawater? After all, Aromat has near infinite seas full of water to supply all of the benzene's needs. Seawater contains, on average, 3.5% salt, made up of predominantly sodium chloride or table salt. Benzenes in humans can't drink salty water because it actually causes dehydration. When you drink salt water, a massive amount of salt enters your bloodstream, and to clear out this excess salt, your kidneys have to produce urine. However, because your kidneys can only produce urine that is less salty than the water you just drank, your body is forced to flush out more water than you actually took in. This causes you to lose crucial fluids and dehydrate much faster, and in extreme cases, it can even be lethal. The benzenes need to find a way to remove the salt from the water. One way to do this is in a lab, is to boil the water and condense the vapours. This creates a stream of purified water and leaves a concentrated salty solution behind. This process is called desalination. On Earth, desalination is used to produce drinking water. Desalination plants now make 135 million cubic metres of water per day. That's 54,000 Olympic-sized swimming pools, or 37 pools every minute. Originally, thermal desalination plants were used, like the one in the lab. However, this process is very energy intense and not always practical. They need to find a way to make this process as cost efficient as possible. The benzenes have designed a reverse osmosis plant to create drinking water from seawater. This starts with collecting water from the sea. They have installed a large multi-lane pipe to suck in seawater from the ocean and bring it into the plant. Each intake will be covered to prevent large objects and fish being carried in with the water. The next stage in the process is to screen the water. A fixed metal guard is positioned in the flow of the intake. This will stop any large foreign bodies that have managed to get into the pipe from continuing into the plant. After primary screening, the water is sent to secondary screening filters. This pre-treatment tank is designed to remove smaller solids that made it through the primary filtration. First, a layer of anthracite. It is light and stays at the top of the filter. It acts as a rough screening layer, trapping the largest suspended solids, algae, and large organic fragments. Then, a layer of quartz sand. This is the main component of the filter. It performs fine filtration, trapping medium-sized impurities, salt, and colloidal matter. The bottom layer is granite or magnetite. This is the densest layer. The tight compaction can remove particles down to 20 microns. There are two filters that are working in duty standby. When one is spent and needs regenerated, the other can be brought online to allow production to continue. Once the water is filtered, it can be sent to the reverse osmosis hall. The theory of reverse osmosis revolves around overcoming a natural thermodynamic process called osmosis, where water spontaneously flows through a semi-permeable membrane towards a higher salt concentration to achieve chemical equilibrium. To reverse this, external mechanical pressure is applied to the salty solution that exceeds its natural osmotic pressure. The artificial pressure alters the system's chemical potential, forcing water molecules to move against their natural concentration gradient, leaving behind the dissolved salt ions as they pass through the membrane to the fresh side. The water goes through one more filtration stage to remove any remaining fine particles. High pressure pumps then force this clarified water into pressure vessels containing tightly wrapped, spiral wound membrane elements. As the water pushes against these membranes, pure water molecules are squeezed through the microscopic layers into a central collection cube as fresh permeate, while the blocked salt and impurities wash out the opposite end as a concentrated brine. Some of the energy from this brine can be recovered. Inside the pressure vessel, a spiral wound membrane works by utilising a multi-layered sandwich of sheets wrapped tightly around a central perforated collection tube. This sandwich consists of a semi-permeable membrane layer, a porous permeate spacer, and a feed spacer. This allows the salty water to flow. As high pressure feed water is pumped horizontally through the element, the feed spacer distributes it across the membrane surface. This pressure forces pure water molecules through the membrane and into the permeate spacer, which acts as a fluid highway, guiding the clean water in a spiral path inwards until it drops into the holes of the central tube as fresh water. Meanwhile, the rejected salt and impurities continue straight out the back of the element as concentrated brine. The brine waste needs to be disposed of back into the sea. Brine waste is highly concentrated and extra salty, containing roughly double the salinity of natural seawater along with trace pre-treatment chemicals. Because this dense, heavy fluid naturally sinks to the seafloor, it risks creating an oxygen-depleted blanket that can smother a marine ecosystem and disrupt the osmotic balance of bottom-dwelling organisms. To mitigate this, modern facilities utilise high-velocity underwater diffusers to ensure rapid dilution. Finally, the fresh water undergoes post-treatment, where it is chlorinated for disinfection and mineralised for taste, before being piped into the municipal drinking water supply. The water can also be stored in large tanks before being sent into the public drinking water system. Thanks to this invention, the benzenes can now grow crops in areas without access to fresh, clean water. This allows them to make areas normally inhospitable easier to live in. The benzenes are new to YouTube, and they want to keep sharing their journey. If you want to see more, consider hitting the subscribe button.